All right, well, good evening and welcome to lecture 18 for MT225. Let's see here. Let's go over to the lecture notes. There we are. All right, so lecture 18. Um, Homework 7. We have homework 7 out. I issued that last Wednesday. That's due on Wednesday night. So I don't really have an official time on there, I suppose. So sometime Wednesday evening would be sufficient. Just email that to me. It seemed to work out okay with the quiz for the most part. I got most everything emailed in that I was able, and I was able to sort of grade it. It's a little hard to mark up. I'm used to, after grading hundreds of thousands of papers with pens, it's kind of hard to grade an image on the screen, but most of you who submitted quizzes, I returned those by email to you. You should have gotten grades on those. If you didn't receive your grade back, let me know, and I'll check into that. There were a few of the addresses that had some difficulty delivering to it first. A little bit of aggressive spam filtering, things like that. But homework 7 due on Wednesday, and I'll open up the floor for questions on that in a moment. Exam 2. So I misspoke there on exam 2. Exam 2's is scheduled for a week from Wednesday. So that would be April 8th. And well, how we're going to do that is I'll just post up the exam on the website. I'll post it sometime that Wednesday, and I'll pick a reasonable due date, I suppose, sometime Wednesday evening. Um, we'll do it just like we were doing it in class. You can use your class time for that. We won't have an official class that night, although I will be available online, so that if there are questions or something like that, so you'd have similar experience to what we'd have in the classroom. If you had a question during the exam, that I might be able to help clarify something, or at least address whatever concern you might have during that. Um, and then quiz 5 results have been emailed. I do also want to mention, it's not in the notes here, but office hours. Usually my office hours are right before class. We're a little less formal on office hours these days, I suppose, but I make myself available. I'm planning on making myself available here before class for about the hour and a half before class. I might not be online, but I'm reachable by my phone. You've got, most of you should have my number. If not, check the syllabus on the website and you can call or text, but I'll try to get on to the online earlier so that if you have questions and want to address them, you have that avenue available. But of course, most of you who know me, you can always just give me a call, send me a text message whenever, and I'll be glad to try to help out as the situation allows. Let's see here. So questions on homework number 7, method of sections. Any questions there?
Yeah, I have one.
All right, go ahead, Kate.
For problem 2, I don't know why, but I'm having trouble picking a spot for my moment equation.
Okay. Let me load that up here. Got to switch different laptop. Hang on. Let's see.
Which problem were you asking about?
It was problem 2.
Okay.
Bear with me 1 second here. All right, sorry about that. A little bit of the old style sneaker net going on here. I don't have these two machines connected, so let me see here. Let me pull up the homework assignment so we can take a look at it. There it is. All right, so there's the homework assignment. And we are looking at, come on now, problem 2. Nice. Let's try that again. 1 second. Technical difficulties. All right. Kidding me, right?
You guys want? I'm in class. Seriously.
All right. Apparently, on this laptop the college gave me, they did not activate Adobe Acrobat, so I can't view PDFs on it without signing in, and I don't have an account. So we'll load up the document version here. All right. There we go. So problem 2. And so the question was about finding the moment equation and where to take the moment. Well, you always want to pick a pivot point that's going to make your moment equation easy. And here we are looking for members B, C, B, F, and E, F. So it's these 3 members here in the center. Can you see my mouse pointer?
Mhm.
Okay, I'm just not sure exactly what's transmitting. I don't see a copy of it. So we are looking for those 3 members there. Now, when you did your sections, did you close off to the left side through A or to the right side through D?
I closed off to the left through A.
Okay, so you closed off through A. So you've really only got 3 choices for your pivot point. You could either pick A, you could pick E, or you could pick B. Let me draw the section out here, just to give you a little bit of a hint along those lines. So we've got joint A, joint B with 1,000-pound load there. And we've got E. We have our reaction forces, RAX and RAY. And then we've got these 3 unknown forces, FEF, FBC, and FBF. All right. So there's what the section would look like, cutting through member B, C, B, F, and EF, and closing off to the left through A. Now at this point, you'd have values for RAX and RAY. You've really only got 3 possible choices for your pivot point, joint A, joint B, or joint E. And we want to make it so that we have the simplest moment equation we can get. Now, joint A, if you picked joint A, you wouldn't have a moment from RAX or RAY. You also wouldn't have a moment for FEF because the line of action of FEF goes through A. You wouldn't have a moment from FBC because its line of action goes through A. But you would have a moment for the 1,000-pound force. That's not too bad. But then you've got this moment from FBF, and that one's going to be a little bit weird. Trying to figure out the moment of this force that's at an angle find out what the perpendicular component of that is or what the perpendicular distance is. That's going to involve some complexity. We prefer, if we're going to take a moment, we want to have lines of action that are either parallel or perpendicular to where we have our pivot point. So it's easy to figure out what the arms are. If you picked joint E, you'd kind of have the same problem. In fact, it would be even worse, because although the 1,000-pound force and FEF and RAX wouldn't have a moment, FBC is at some weird angle and FBF is at some weird angle. So that would tend to make the moment equation kind of difficult. Joint B is probably your best bet to pick for a pivot point, because you're going to knock out the 1,000-pound force, you're going to knock out FBC and FBF, and those are the ones that are at weird angles that would be hard to find a moment for. FEF will have a moment, but it's not too hard to figure out what the arm is for that, because we need that perpendicular distance. So finding out the arm for FEF isn't too hard. And RAX and RAY, same deal. The lines of action and the arms are pretty easy to sort out there. So joint B looks like it's going to be the best place to go for that one. Does that help out, kid?
Yeah, that helps. Thanks.
All right. Any other homework questions? Let's see. There we go. We had problem 1, 2, and problem 3. All right. Well, on Wednesday night, I'll open up the floor to one of those questions to be worked out at that time. So let's go ahead and move on then, and we'll go back to the class notes here. There we are. So today our topic is to look at another type of structure, what we call a frame. Frames are similar to trusses in that they provide a way for applied loads to be transmitted to supports. That's really all a truss did. A truss allowed us to apply a load in some position, at some position or multiple positions, and transmit that load in various ways through the structure to the supports. A frame does the same thing, but a frame relaxes some of the constraints that we had on trusses. One of the constraints we had on trusses was that you could only apply loads at the endpoints of a truss member, that the truss members were so-called two-force members, meaning that if you knew the direction of the member, you automatically knew the direction of the force. A frame allows us to put the load anywhere we want. And it's a bit of an exercise in working with non-concurrent force systems. So unlike method of joints and method of sections, we're not going to have a number of different methods to solve a frame. We've really only got one way to work out a frame, and that's to treat it as a structure in equilibrium. We're going to apply the same kinds of principles we used with trusses, in that the truss is in equilibrium, so all parts of the truss must be in equilibrium. In the frame, we can break the structure apart into its individual pieces and solve the equations of equilibrium for each individual piece. So with a frame, we have a generalization of the truss that allows multiple force members. What that means is that the forces at the end points of the truss of the frame members are not necessarily aligned with the direction of the member. And I'll show you what that means here as we work out an example. So we can apply a force at any point along the member. So we don't have to worry about only applying forces where there are joints. We can be a little more general about it. But as things get more general, they get harder to compute. So to calculate. So we can't go too far with relaxing these constraints with the tools that we've got available. But we can apply a force anywhere on the structure we want, including in the middle of the member. So in a two-force member, like what we built our trusses out of, forces were only exerted at the ends of members, at the joints. Now, frames are pinned together, just like trusses were. Trusses had pins at each joint that held the members together. And it's those pins that we are interested in figuring out in a in a in a frame. We want to know the total force acting on the pins. Now the difference with trusses was that we only needed one force because the direction was nailed down from the direction of the member. The direction won't be necessarily clear in a frame member. In a frame member, we can have both horizontal and vertical reactions at every pin. Essentially, we can treat each pin like a hinge support, like one of those little triangle supports that has a reaction in both the X and Y direction. And we can figure out what the total force is by looking at the magnitude of those components by squaring them and adding them together and taking the square root. In fact, that's our final answer in any frame problem, is we're looking for the net force on each joint or each pin. So to analyze a frame, we break the structure up into individual frame members. Since each member must be in equilibrium, then each member must have the sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point must all be 0. So that gives us 3 equations, and we can solve for 3 unknowns. In fact, we're going to be a little more flexible than we have been in the past with solving those 3 unknowns. In fact, we'll get into situations where, at least temporarily, we may have more unknowns than we have equations, and that's okay. We will learn how to deal with that. Fortunately, the math isn't actually that difficult, and we very rarely, if you set it up properly, if you work with a truss problem or the frame problem carefully, you should never have to take a sine or cosine in working with any of the frame members. And I'll show you some ways to approach these problems to keep the math as simple as possible. So we're going to follow a sequence that's pretty similar to that we'd use for a truss. We'll first solve the external problem, and then we'll figure out what goes on inside at the pins specifically. I think the best way to really take a look at how this works is to work through a problem. So let's start with this one here. Here I've got a frame, and I can tell it's a frame because it's being loaded in places that we wouldn't normally load a truss. A truss, for example, is typically loaded at the joints. Whoops. They're loaded at the joints. So here we have joint A, joint B, joint C. The load, if this was a truss, could only be applied at joint A, at joint B, or at joint C. Here we've got a 200 Newton load pushing down in the middle of the beam. And if you think about what that does to the forces, to the reactions, the supports at A and B, if you're pushing down in the middle of this beam, then the supports at either end are going to have to be pushing up. That's automatically different than what we've seen with trusses. With trusses, we always knew what the force direction was going to be. It was going to be right along the direction of the truss, or the direction of the member. When we load up a frame, we're putting the load on points that we normally wouldn't in a truss, and that makes the loading more complex. We can't even say, for example, that member AB here is in tension or compression. It's actually in both. It's bending. Bending is a much more complex state than tension or compression. So what we've got here, I'm going to annotate this just a little bit here, is I've got these 3 joints. I've got joint A right here. That's where we've got a pinned support. I've got joint B, which is really the only internal pin in the member, or in the frame. It's the pin holding these 2 members together. And then we have this support down here at C. Those are where the forces are. Now, the way we start these problems is the same as all the others. We solve the external problem. And so I'm going to translate this over onto my page, and I'll switch over. We've got these two members. And for the external problem, we don't have to worry about anything going on inside. All we have to worry about are the forces that are being applied. So we've got our 500 Newton force pulling to the right at the top of member BC. And then we've got at the middle of member AB, we've got 200 Newtons. So switching over here to the to my paper, here we've got our frame members. We've got the two frame members there. This is joint B. We have A and C here. And let me see here. Did I get the labeling right there? Yeah, A and C. At A, there is a pinned support. And in our truss problems, we learned that when we replace a pin support, when we're drawing a free body diagram, we replace the pin support with two forces. And we'll call that RAX and RAY. Now C also has a pinned support on it. If we go back to the slides for a minute here. C also has a pinned support. That's kind of weird. We've never had two pinned supports in a truss before. And in fact, in a truss, it's a problem. It's a difficult problem. You can't have, at least with the math that we're doing, you can't have two pinned supports in the same problem. But in a frame problem, you can. And we always replace that pinned support with two forces. So at C, since I have a pinned support, I'm going to call this RCX and RCY. So this is the external problem. And once you've solved enough of these, you start looking ahead a little bit and thinking about how you're going to do the solution and whether or not you can actually solve the problem. We can get three equations out of this. The sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point are all 0. Three equations buys us the ability to solve three unknowns. But I've got four unknowns in this problem. I've got RAX, RAY, RCX, and RCY. That's four unknowns. Now, it doesn't mean that we can't solve the problem. It means that we're not going to get numbers for all the unknowns right away. When you have three equations, what that tells you is that you've got three relationships that the unknowns have to satisfy. Now, if you're lucky and you have exactly the same number of unknowns as you have equations, then that means you're going to get numbers for each of those values. They'll tell you exactly what the numbers have to be for the unknowns. But if you have more unknowns than you have equations, then what you're going to get is not necessarily a number, but a relationship between the unknowns that has to be satisfied. And that relationship can be carried forward into other parts of the problem. As long as we're careful about how we draw things, and a little bit of we take a little bit of care with Newton's third law, we can use that information. So although we might not get a number, we will get some information that will eventually be useful. So let's go ahead and form the equations and see what happens. So we've got our sum of forces in the x direction. So going through and tabulating out our forces in the x direction, we've got RAX, and that's positive. We've got this 500 newtons to the right, so that's also positive. And the only other x direction force is down here at C. That's RCX. Also pointing to the right, so it's also positive, since to the right it's positive, up is positive, and counterclockwise moments are positive. So our sum of forces in the x direction would have to equal 0. If we take our sum of forces in the y direction, we've got a positive RAY. We've got a negative 200 newtons. And then we've got a positive RCY. Those are all of our y direction equations, or all our y direction forces. So that's got to equal 0. And then we've got to pick a pivot point for our moment equation. And it's almost always a good idea to go for one of the support points. You knock out 2 of your unknowns that way. Any other point, you might not knock out all those unknowns. Let's go ahead and pick, well, I think we'll pick joint C. It's at the bottom. So we'll pick joint C for that one. So we'll take our pivot at joint C. That means RCY and RCX will not have moments. But the 500 Newton force up here is definitely going to have a moment. If we pin it at C and pull up there at the top, there's definitely going to be a clockwise rotation there. We've got this 200 Newton force. That's got an arm compared to joint C, so that will have a moment. RAX, it has an arm compared to C, so RAX will have a moment. And RAY will also have a moment. So we're going to end up with 4 unknowns in our moment equation. So we've got 4 unknowns in the moment equation. For our distances here, this distance was 6 meters. It was 5 meters from C to B, and then 1 meter up. So that's 6 there. And then we had 2 meters and 2 meters there. So the arm for the 500 Newton force is 6 meters. So I have 6 times 500. Pinning at C and pulling up there is going to cause a clockwise rotation, and clockwise rotations are negative. The 200 Newton force, its line of action is 2 meters away from joint C. So we have 2 times 200. If we pin at C and pull down here at the 200 newtons, that'll cause a counterclockwise moment, so positive. Then we've got RAX. RAX is 5 meters from C. The line of action for RAX was 5 meters from C. So we have 5 RAX. And if we're pushing to the right, that'll cause a clockwise rotation, and clockwise rotations are negative. And then we have RAY. RAY's line of action is 4 meters from C. So we have 4 RAY. Pinning at C and pushing up at A would cause a clockwise rotation, so that's negative. So if we look at the equations we've got here, we've got a bit of a problem with all these equations. We can't solve any of them right now. But we do have some relationships now between the unknowns. We have RAX plus 500 plus RCX is 0. We could clean that up a little bit by saying RAX plus RCX equals negative 500, subtracting the 500 from both sides. We could clean up the y direction equation a little bit by adding 200 to both sides and saying RAY plus RCY is 200. And we could clean up the numbers a little bit here. Negative 6 times 500 negative 3,000 plus positive 400 minus 5 RAX minus 4 RAY. and that equals 0. So we have a negative 2600 minus 5 RAX minus 4 RAY. And I could add the 2600 to both sides and make that negative 5 RAX minus 4 RAY equals a positive 2600. Now, unfortunately, the way these four unknowns are set up, we really can't combine these together. There's really not a way to combine the rest of the equations together. We don't even really have simultaneous equations here. We just have different sets of our unknowns. So it might look like we've got some problems as far as proceeding, but we'll see here in a moment that we can get some extra information from looking at the other members in the frame that will give us enough information to let us unwrap everything that's going on here. So from this stage of the problem, from the external problem, in this one, we didn't get any numbers, but what we got were three relationships amongst our unknowns. We have that RAX plus RCX equals a negative 500. RAY plus RCY equals a positive 200. And negative 5 RAX minus 4 RAY equals 2600. That is essentially a little equation bank that we can carry forward with us, that we can use later on. These are relationships that these unknown quantities have to satisfy. And as soon as I get one of these values, if I get the value of RAX, for example, I can solve this top equation for RCX. Once I've got a value for RAX, I can also solve for RAY, and once I know RAY, I can solve for RCY. So everything collapses, everything solves once I've got one of these values. So I just need to figure out one of those values from another step in the problem. So at first here, it doesn't look like we've really accomplished much. But what we've done is we've established three relationships that four of our unknown quantities have to satisfy. Now, in the end, what we're looking for is a table. Just like in the trust problems, we're looking for a table. But the table in this case has a little bit different information in it than we had with the trust problems. We have our joints, in this case, A, B, and C. The pins in the problem or the supports in the problem. What we're going to get are X and Y components of forces that are at each pin. We'll see in a moment that the values we get here for the X and Y components are going to depend on our assumptions. When we drew our free body diagram, for example, here, we made some assumptions about the directions of the reactions at A and C. The sign that we get, whether we get positive or negative, is going to depend very sensitively on those assumptions. Different people are going to get different signs for those, and that's okay. Because in the end, what we're looking for is the magnitude. We want the total force acting on those pins. And remember what the magnitude is. The magnitude is the square root of the squares of the component, the squares of the values. So we have x squared plus y squared. Because of these squareds, it won't matter whether we have positive or negative values here. So you might make different assumptions than I make, and that might cause you to get positive or negative values for x's and y's. When you square those, the signs go away. So the magnitude should always be the same. So if you're working one of these problems and you're going to compare to my answers or to your neighbor's answers or your classmates' answers, don't compare the individual x and y values because you might differ up to a sign in that. What you get positive, your classmate might get negative. But the magnitudes will always come out the same. The magnitudes don't depend on the sign. You square that, the sign goes away. So at this point, we can't really fill anything in on the table. But we've got three equations that we can use, and I'm going to translate those over here. RAX plus RCX is a negative 500. RAY plus RCY is a positive 200. And negative 5 RAX minus 4 RAY is a positive 2600. So while we may not have numbers that we can fill into our table, we've got equations we can solve. Later on, we've got relationships between our unknown values. So how do we go any further? Well, the way we go further is by looking at the individual members of the frame as separate bodies in equilibrium. I can draw the free body diagram of member AB here, for example, and it would look something like this. Member AB has RAX and RAY on it, which we still don't know, but be careful, make sure you make the same assumptions for your supports. I assumed to the right and up, so I've got to assume the same here with RAX and RAY, otherwise these equations over here won't work. And then I've got this pinned support B. That pinned support B is another pin, so I can replace the forces that the pin supplies on that member with two forces. I can say RBX, or that would be RBY, and RBX. And I'm following kind of my basic rule of thumb here with identifying unknown quantities. Unless I have information to the contrary, I always assume positive. So I assumed RBY is pushing up on member AB, and RBX is pulling to the right. There's a reason for that I'll come to in a moment. So that's, once I put the 200 newtons in here, that's the free body diagram for member AB, for the horizontal member. We also need a free body diagram for the vertical member. And this is someplace we have to be very careful. And it'll make sense after a couple of problems, but let me show you how to draw that free body diagram. What I'm doing is I'm exploding the structure. I'm taking it completely apart. I'm separating the two members that we had in the original structure to two separate members. And one of the things we have to make sure of is that those two members will fit together properly. We know the direction there for that 500 newtons. If I look at the assumed directions I've already made here for RCX and RCY, those have to be to the right and up. So I'll put those in here. RCX and RCY. But here's where we have to be very careful. And this is the make or break point in the problem. Joint B is unique in this problem because it's the only internal joint. It's the only joint that's shared between both members. Joint A is only on member AB. Joint C is only on member BC. But joint B is shared between the two. And that means that we have to be very careful about how we draw the forces that are involved. Because joint B is applying force to both members. Essentially, the force that one member exerts on joint B, that force from joint B then gets exerted onto the other member. We can't just draw whatever we want here for the forces at joint B, because we've already made some assumptions up here about the directions of the forces at joint B. what we have to take into account only on shared joints, only on joints that are shared between multiple members, is we have to take into account Newton's third law. Remember what Newton's third law says. It's the law of action and reaction, that we have equal but opposite forces. When we draw two free body diagrams that are connected at one point, the forces at that shared point have to be equal but opposite. So to make this consistent, to make this diagram right, I have to draw my y direction force down, because I assumed my y direction force was up in the other drawing. I have to draw my x direction reaction to the left. Now I keep that straight for myself by always drawing the first time I see a joint, always drawing the reactions positive, independent of whether my intuition says it's going to go to the left or the right. Again, remember, the signs aren't going to matter so much here. That way I know if I see that joint again in another member, I have to draw it opposite. The second time I see that joint, I've got to draw opposite direction. So I draw positive the first time I see the joint. I draw negatives the second time I see the joint. That way I always make sure I satisfy that equal but opposite idea, Newton's third law. Another way to see that is by putting these two together. If you think about reassembling this drawing, remember when you are assembling something, most of you are A&P students or former A&P students, when you're assembling parts, you've got to have parts that fit together. You've got to have a nut and a bolt, parts that would be able to connect. Here we have forces that are equal but opposite when they can connect together. They're not forces in the same direction that would oppose each other, or that would like trying to put two bolts together or two nuts together. The equal but opposite kind of makes it look like these two should fit together right at that point. So that's the trick. That's the part that gets people into trouble when dealing with frame problems. When you draw the free body diagrams of the members, you have to make sure that on shared joints, and only shared joints, you draw equal but opposite forces. So same symbol, different direction. So positive, I do it by drawing the first time I use that member that joint in a member, I draw it positive, and then the second time I draw it negative. That way I never mess them up. The external supports always are going to be just once. You don't share at the external supports. There are no shared joints there. It's only at the internal supports, the joints that are shared between members, that you have to worry about that. Now, that being said, we can now proceed with the problem. We've got two free body diagrams here, and we can do sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. And in fact, it's going to turn out that we're only going to need one of these two. In this problem, it ends up being that we only need one out of these two. In other problems, we might need more than that. It depends on how many unknowns we've got. In fact, that's a nice thing to be aware of here. If you look at the table that we've really got 6 unknowns in the problem. We've got the x and y components at A, we've got the x and y components at B, and we've got the x and y components at C. To solve for 6 unknowns, we need 6 equations. Well, we got 3 equations from our external problem. We're going to get the other 3 equations we need from one of these two. And it doesn't matter which one we use. So I'm going to pick arbitrarily here the horizontal one to use. If I pick the horizontal free body diagram, my sum of forces in the x direction are going to look like RAX to the right, so positive RAX, and positive RBX. So RAX and RBX, those are my only x direction forces. I have my sum of forces in the y direction. I've got a positive RAY, a positive RBY, and a negative 200 newtons. And then I've got my moment. And I think I'll pick joint A for that one. And remember the distances we had here. We had 2 meters and 2 meters. If I pick my pivot point at A, RAX and RAY won't have a moment. RBX will also not have a moment because the line of action of RBX goes right through joint A. The only two forces that'll have a moment are RBY and the 200 Newton force. So let's figure that out here. We've got the 200 Newton force 2 meters away, so we 2 times 200. Pinned at A, pushing down at the 200 Newton force, clockwise rotation, so negative. And then we have RBY 4 meters away, so 4 RBY. Pinning at A, pushing up at B, we're going to get a counterclockwise rotation, so positive, and that equals 0. So we get another 3 equations. One of those we can solve right away. We can solve the moment equation now. If we simplify it down a little bit, we have negative 400 plus 4 RBY equals 0. If we add 400 to both sides, we have 4 RBY equals a positive 400. And dividing both sides by 4, RBY comes out to be 100. So we've got a number now that we can fill into our table. Finally, we've got RBY is 100. Now that we know that, we can go ahead and figure out what RAY is. We can go to the y direction equation. RAY plus 100 minus 200 equals 0. 100 minus 200 is a negative 100. So we have RAY minus 100 is 0. So RAY, if we add 100 to both sides, RAY must be 100. So there's another one we can fill in. We have RAY is a positive 100. Now, unfortunately, we don't have RAX or RBX. So that equation is going to have to go into the bank over here. RAX plus RBX equals 0. But if we look at our equations now, we've got some information we can use. We know RAY. And now that I know RAY, I can solve the RAY plus RCY equation. Should also be able to solve that moment equation. And that's going to give us something that we can work with. So we'll be able to find RAX and find RCY, and then we'll be able to use that information to find everything else. So once we've got one number, everything else just kind of starts falling apart. So let's go ahead and solve some of these here. We've got RAY plus RCY. RAY is 100. So using that equation right there, RAY is 100 plus RCY equals 200. Subtract 100 from both sides, RCY equals 100. So RCY is 100. Working on the on this equation, if we bring that one down here, RAY is 100 according to our table. So if I plug that in here, I've got negative 5 RAX minus 4 RAY. RAY is 100. Is 2600. So we have negative 5 RAX minus 400 equals 2600. Add 400 to both sides. I get negative 5 RAX equals a positive 3000. Divide both sides by negative 5. And RAX equals negative 600. So RAX is a negative 600. So we can go back up to the table and fill that in. RAX is negative 600. Now that we have RAX, we're only missing two pieces now, RBX and RCX. If we go to this first equation, RAX is negative 600, so we should be able to find RCX. We have negative 600 there, plus RCX equals negative 500. If we add 600 to both sides, RCX is going to equal a positive 100. And RAX plus RBX equals 0. So we have negative 600 plus RBX equals 0. So RBX must be equal to 600. So there we go. We've got X and Y components. We've solved for 3 support forces, 3 X and Y components at joints A, B, and C. To finish up the problem, we need to get our magnitudes. And the magnitudes are the X component squared plus the Y component squared, square root. Save yourself some trouble when you find your magnitudes. Ignore the signs. I see a lot of people mess up with their calculators trying to key in the signs and forgetting that in certain calculators, when you key in a sign, if you don't use parentheses, then the square doesn't see the sign and you end up burning yourself. If you understand that any number you square, whether it's positive or negative, comes out positive, just ignore the signs when you go to square it in your calculator. So I won't even enter negative 600. I'm just going to take 600, square it, add it to 100 squared, and take the square root. And that gives me 608.28. And these are all in newtons. And have the same here for B, 608.28. And then we've got 100 squared, 100 squared, plus 100 squared, which is 141.42 newtons. So our final answer here is this table with these 3 magnitudes. You can think of the magnitude here as the total amount of force, the net force on each of those pins. The pin at A, the pin at B, and the pin at C. That's the amount of force trying to shear through that pin. And that would be important to know if we were going to build this structure. We'd want to know how much force is trying to shear through it, because that would tell us about how big we need to make it, or what material we need to make it out of. So there we get 3 magnitudes, 608.28 newtons for A and B, and 141.42 newtons at C. So that's a frame problem. Now the big takeaways is the biggest takeaway from a frame problem, the biggest difference to keep in mind when you're working a frame problem is that you will end up with equations you can't solve right away. Put them into an equation bank and come back to them when you've got enough information. You're not guaranteed anymore to get everything you need in one step. You may have more unknowns than equations. Now, there is some path dependence here. There is some difference in what you get for the signs on your table, depending on what order you do things in. That's okay, because in the end, all we need is that magnitude. And that, again, has something to do with the assumptions that you make. So in the end, make sure your magnitudes match. Your signs may not necessarily match on the individual components. And bear in mind that little issue there when you're drawing free body diagrams involving a shared joint. The joints have to have equal and opposite forces in those corresponding free body diagrams. So Anyone have any questions so far? All right, let's try another one here, and we'll work through the same process, but this time it's a little bit more sophisticated of a problem. You'll see though that the math doesn't tend to work out to be too difficult because we're looking at x and y components. Sines and cosines are almost something we never have to deal with in these types of problems. So that's at least a bit of an advantage. So the math doesn't tend to get too difficult as long as you can handle the equations that show up. So let's go back to the notes here, and we'll take a look at the next problem. There we've got a little more sophisticated problem. It's looks a lot like some sort of chair or something like that, I suppose, maybe like a stroller or something. It's got a pinned support at A. It's got a roller support at E, but then it's got three members that make up the frame. We've got member AC, the vertical member here. We've got BD, the horizontal member, and we've got this slanted member CE. Now, one piece of advice that I'll give you in working with these problems is you do have some choice about the order you go in and what free body diagrams you use and what ones you don't. Try your best to avoid doing the free body diagram or dealing with the free body diagram of a slanted member. Horizontal and vertical are always the best way to go. The reason for that is when you pick a pivot point, no matter what end you pick, you're always going to knock out at least one of the forces at the other end. In a slanted member, that's not going to be the case. In a slanted member, the forces at the other end will always generate moments, and that makes the moment equation a little more complex. So my usual approach to handling these kinds of problems is to avoid ever working with the free body diagram of a slanted member. So let's look at the problem that we've got here and count up the unknowns. We have a pinned support at A. So we've got a pinned support there. That's two unknowns, an X and a Y component. We have a pinned support at B. That's two more. So four total so far. We've got a pinned support at C. So we've got six unknowns now. We've got a pinned at D. That's another two, so eight. And we've got a roller at E. Rollers only have one unknown. So we have a total of 9 unknowns here. The X and Y reactions at A, B, C, and D, and then just the Y reaction at E. So in building up our table, we're going to have 5 columns or 5 rows in our table. We'll have our X and Y forces, and since our forces are in pounds in this one, I'll label the column headers in pounds, and we'll have our magnitude. But we'll have one for each joint, so A, B, C, D, and we'll add in one for the roller, although I'll shade out or cross out the box for the X component on that. So if I switch over here to the camera, there's my table, A, B, C, D, and E. I won't have an X reaction at E because E is a roller. It's only going to have a Y reaction perpendicular to the surface it's on. So there's my 1, 2, 3, 4, 5, 6, 7, 8, 9 unknowns. Now 9 unknowns, that's 3 sets of 3. That means we're going to have to do 3 free body diagrams. If you remember back to when we did method of joints, I said that if we had a 5-joint member or 5-joint truss, we would have to solve 4 of the joints. We'd have to solve 1 less than what we'd have, than what we had available. It's the same kind of idea here, if we go back to the display, we've got 4 possible free body diagrams we can draw, but we only need 3 of them. Each free body diagram gives us the potential for 3 pieces of information, 3 unknowns. We've got 9 unknowns, so we only need 3 sets of 3. We could use a free body diagram of member AC. We could do a free body diagram of member BD. We could do a free body diagram of CDE. Those are 3 of them. But then we've also got the external problem, treating the whole truss or the whole frame as one solid object. That's a 4th free body diagram. Use that flexibility. The fact that you only have to do 1 less than the possible number of free body diagrams you've got to avoid doing things like working this slanted member. So what I'm going to do here is I'm going to solve the external problem first. That'll pick me up some information about A and E. And then I'm going to do the free body diagram of member AC and the free body diagram of member BD. Those will pick me up the remaining 6 unknowns, and I won't ever have to do anything with member CDE. Now, it's not to say you couldn't. You could certainly do the free body diagram of member CDE, but generally, free body diagrams and the equations that result from a slanted member tend to be more complex. So if we can avoid working with that, we certainly can. We'd certainly prefer to. It's not always possible. In fact, I think on our next homework assignment, I've got one for you to work on that requires that you work on one of the slanted members. But for now, we'll avoid that. So let's do the external problem first. So I'm going to sketch down the information from the drawing and draw the external free body diagram. We've got right here 1 foot above joint A. I've got this 43.5 pounds. And let's see, that's 1.5 feet. All right. So here's my free body diagram so far. I've got my x direction reactions, RAX and RAY at A. I've got REY at E, only a Y direction because it's a roller. And then I've got the 43.5 pound force there. There's 1.5 feet between those 2 points and 1 foot like that. Now there's a benefit here. Look at how many unknowns we've got in the problem at this point. We've got 3 unknowns, RAX, RAY, and REY. I'm going to get 3 equations. When you have 3 equations and 3 unknowns, when the number of unknowns matches exactly the number of equations, you're guaranteed numbers. So we're going to get numbers out of this for RAX, RAY, and REY. So let's do our sum of forces in the x direction. I've got positive 43.5 pounds, since that's to the right. I've also got a positive RAX. No other x direction reactions. We take our sum of forces in the y direction. I've got RAY plus REY and nothing else. There's no other y direction forces. And then we've got our moments about a point. And I'm going to pick my pivot point to be joint A. Since everything seems to be nicely measured from there, seems like it'll be easiest. That'll knock out RAX and RAY, but the 43.5 pound force will have a moment, and REY will have a moment. The 43.5 pound force is 1 foot away, so that's 43.5 times 1. Pinning at A and pushing to the right, that'll cause a clockwise moment. Clockwise moments are negative. And then we've got REY 1.5 feet away. So I have 1.5 REY. Pinning at A and pushing up at E will cause a counterclockwise rotation, so that's positive. So that moment equation we can solve pretty quickly. We can add 43.5 to both sides. That'll give us 1.5 REY equals 43.5. And dividing 43.5 by 1.5 gives us 29. So REY is 29 pounds. So now we've got something we can fill in on our table. We've got 29 pounds. And of course, if you've only got one component, that's the magnitude. So at E, 29 pounds. So I've already finished up my row at E. Knowing REY, we can go ahead and figure out RAY. Since RAY plus 29 pounds equals 0, RAY must be a negative 29 pounds. So RAY is negative 29. And we can solve our x direction equation just by subtracting 43.5 from both sides. RAX is negative 43.5. So negative 43.5. So we got three numbers there. So we solved the external problem. We've knocked out three of our unknowns. Now we've just got three of them, or six of them that we've still got to figure out. The internal pins need to be figured out. And I'll come back at the end here and find the magnitudes. The 29 here was easy in the last one, so I did that automatically, but the others we'll calculate when we're done. Any questions so far? All right, so let's
Hold
go.
on. I think I missed something here.
Okay.
At the A in the Y direction, the A, you have a negative 29, and then in the E, it's a positive. Where did that negative 29 come from?
From the Y direction equation right here.
Oh, okay.
We figured out REY was a positive 29. RAY plus REY needs to equal 0. So
Aha.
solving that, the only thing you can add to 29 to make it 0 would be a negative 29.
Okay, got it.
All right. Any other questions so far? So let's look at the free body diagrams first here. I'm going to flip over to another page and then we'll pick which free body diagrams we want to work with. So let's just draw out what the free body diagrams will look like. And here it's a good idea to keep the same basic assumptions you had in your external problem. So there's the original structure. I have A, B, C, D, and E. I have my pin and my roller. And what I'm going to do here is blow that structure up. I'm going to separate it apart. I have this 43.5 pounds over here. So this was the picture that's in the notes, minus the geometry. I'm going to blow this apart into three members. So there's the vertical member. Over here is the horizontal member. And then over here is the slanted member. So I've got A, I've got B and C, I've got B and D, and then I've got C, D, and E. What I would encourage you to do at this point is to copy over the assumed directions you had for RAX, RAY, and REY. You want those to be the same so that when you plug in your values for RAX, RAY, and the 29-pound force, or an REY, that everything works out okay. you've already tied yourself into these assumptions. That's why these signs came out the way they did. If you flip the assumptions now, you're going to get confused in your signs. So keep the directions all the same for your external forces, for your reactions. That way you can import the information you figured out in your first step a little more easily at the end without getting confused in signs. So I'm going to keep everything symbolic for now, and then we'll come up with the equations and plug in as we need to. So I had RAX and RAY, and I had REY. And now I'm going to follow the same rule that I mentioned earlier. Every time I see a joint, if it's the first time I'm seeing that joint, I'm going to label the forces as positive. The next time I see that joint, I'm going to flip them over and make them negative. That'll make sure that my equations will be consistent from one member to the next. So at joint B, I've never seen joint B before, so I'm going to put RBX and RBY. I've also never seen joint C before, so I'll have RCX and RCY. For the horizontal member, I've seen joint B before. So I have to be careful about how I'm drawing that. In fact, I'm going to scribble this out here. I know it's a little messy, but I need a little more room. So I'm going to put it down here. B and D. I've seen joint B before. So I'm going to flip the directions on the forces. RBX, because I'm using the same symbol, RBX, but they're equal and opposite forces. So I have to make sure they're going to fit together. So RBX and RBY will be opposite, since I've already seen joint B before. I've never seen joint D, or at least I haven't seen joint D yet, so I'll assume positive. RDX and RDY. And then in the free body diagram for the slanted member, since I've seen joint C before, I'll assume negatives. RCX and RCY. And since I've used up joint D already, or I've seen joint D before, I'll also do negatives. RDX and RDY. Those are the three free body diagrams for the frame members. Because I've already got 3 of my unknowns solved for, I only need 2 of the remaining of these 3 free body diagrams, because I have 6 unknowns left. That means 2 sets of 3 equations. I'm going to go with the horizontal and vertical ones. But if you find yourself getting into trouble with directions and all of that, or you're not sure what free body diagrams to use, draw all of them and then pick and choose which ones you want to use. So I'm going to use the horizontal and the vertical ones. Anything not quite making sense about the directions of forces that I've drawn here for these 3 members? All right, so I'm going to copy over the vertical member first. So our vertical member, we had A, we had B, and we had C. I forgot the 43.5 pounds there too. That's on there. All right. So I've got RAY, RAX, and RAY. I've got the 43.5 pounds. I've got RCX and RCY. And I've got RBX and RBY. So there we go. Looks the same as what I had up there. Although there are a lot of symbols in there, keep in mind we have numbers for RAX and RAY. So when we write up our equations, we'll be able to substitute in some information. So let's do our sum of forces in the x direction. In the x direction, I've got a positive RCX. I've got a positive RBX. I've got a positive RAX. And I've got a positive 43.5 pounds. And that equals 0. In the y direction, I've got a positive RAY. I've got a positive RBY. I've got a positive RCY. And that equals 0. And then I've got my pivot point. I've got to pick a pivot point. And you might be tempted to pick joint A. But remember that we know RAX and RAY. It's better to have a moment that you know than a moment that you don't. So I'd rather pick joint B or joint C as my pivot point, because then I'm going to knock out two of my unknowns and hopefully end up with an equation that I'll be able to solve, rather than end up picking it down here, knock out two forces that I already know, and end up with an equation I might not be able to solve. So I'm going to pick joint C as my pivot point. If I pick joint C, it's going to knock out RCX and RCY. It's also going to knock out RBY and RAY, since their lines of action all go through C. But I will have a moment from RAX, but that's just going to be a number. I will have a moment from RBX, and I'll have a moment from the 43.5 pounds. I'm going to need some geometry for that. The way that it worked out here was the heights. We had 0.667 feet and 1.333 feet. And then this was 1 foot. So for my moments, you have to do a little bit of translation to make sure that you've got the right values for your arms. From joint C down to joint B, that's a distance of 1.333 feet. So I have 1.333 RBX. And if I pin at C and pull to the right at B, that's going to be a counterclockwise moment, so positive. So positive 1.333 RBX. RAX is a total of 2 feet away, 1.333 plus 0.667. So that's 2 feet times RAX. And based on the directions I've drawn, if I pin at C and push to the right at A, I get a counterclockwise moment, so that's also positive. And then I've just got to figure out my distance to the 43.5. But if we're from C to A is 2 feet, and it's 1 foot back up to the 43.5, it must be 1 foot distance there as well. So the 43.5 is 1 foot away. So we just have 43.5 times 1. Pinning at C and pushing to the right, that's also counterclockwise, so also positive. So there we've got our moment equation. Now we can plug in some information. We know what RAX and we know what RAY are. We know what those values are. So we can plug those in wherever we see them. RAX was negative 43.5. Keeping the sign, because I made the same assumptions for directions down here, I can keep the signs whatever I found here. It's simplest that way, rather than trying to get confused about directions and correcting the direction and all of that. Keep the same assumptions and just use whatever signs you got. So RAX is negative 43.5. So we've got negative 43.5 there. And we've got negative 43.5 there. We also have RAY is negative 29. So we have a negative 29 there. The negative 43.5 and the positive 43.5 here cancel each other out. So that just gives me a new, simpler equation that RCX plus RBX equals 0. Over here, I could add the 29 to the negative 29 to, or add 29 to both sides and get a slightly simpler equation, RBY plus RCY equals 29. And then down here, we've got a little bit of math to do. 2 times 43.5 is 87. So we have 1.333 RBX minus 87 plus 43.5 equals 0. 1.333 RBX minus, if you add negative 87 and positive 43.5, you get a negative 43.5. Add 43.5 to both sides. And we get 1.333 RBX equals 43.5. Divide both sides by 1.333. And RBX comes out to be 43.5 divided by 1.333, 32.633. That's pounds. So we've got another number we can plug into our table. RBX is 32.633 pounds. It also lets us solve for RCX because we can now go up to the x direction equation and plug in RBX. We have RCX plus 32.633. Subtracting 32.633 from both sides, RCX is negative 32.633. So we pick up RCX also as negative 32.633. Unfortunately, we're left with that y direction equation. We don't have enough information to solve for that. We don't know our by, we don't know our cy, but we know something that has to be true for those values, that whatever our by and our cy are, they have to add up to 29. While that's not as nice as having a number, at least it's a piece of information. It's what we call in the business, we call it a constraint. We call it something that must be true. It keeps our by and our cy from just being any old numbers. They have to be two numbers that add up to 29. That's more restrictive than just having those be any two numbers whatsoever. So it's a constraint on the system. And constraints are good because they give us, they restrict the possible solutions. They reduce it from being an infinite number of solutions to being a smaller number, hopefully down to the point where we can get a unique solution, one answer. But that's all we can get from our vertical member. So from the vertical member, and we might have suspected we weren't going to get numbers out of everything because we had 4 unknowns here. We didn't know RCY and RCX. We didn't know RBY and RBX. 4 equations, or 4 unknowns, only 3 equations. That means we're likely to get something that doesn't involve a number. If we're very unlucky, we get 3 equations we can't solve. If we're luckier, we get 1 or 2 numbers and 1 or 2 equations. Here we got 2 numbers and 1 equation. So that's better than the alternatives. Any questions on the vertical member?
Yeah, so interesting. Okay, disregard.
All right, any other questions on the vertical member? All right, let's take care of the horizontal member then. The horizontal member, I gotta find my sheet here. Found it. Oh. There we go. So the horizontal member is pretty simple. And in fact, I'm going to go ahead and just use this sheet, and then we'll go back to the table. Here's my horizontal member's free body diagram. So I'll redraw that down here, so it's a little clearer. I have r dy and r dx. We have r bx and r by. Now here it looks like we've got 4 unknowns, but we actually don't. We have 3 unknowns because we already know what rbx is. So we've got 3 unknowns. We're going to get 3 equations, which means we're going to get numbers for our 3 unknowns here. And then once we know what rby is, we'll be able to go back to this equation and get rcy. So we've got our solution pretty much surrounded here. We do have to have a length in here. This is 1 foot, so no big deal there. So let's do our equations of equilibrium. Sum of forces in the x direction. I've got a negative rbx plus a positive rdx. That equals 0. I'll do my sum of forces in the y direction. I've got a negative rby and a positive rdy. That equals 0. And then we've got moments about a point. Either endpoint would be a fine place to go. They're both going to give you the same bit of information. So I'm going to pick B as my pivot point. That means no moment from rbx or rby. Also no moment from rdx, because rdx has a line of action that goes through B. Rdy is going to be the only force with a moment. And it happens to be 1 foot away, so it's 1 rdy. Counterclockwise, so it's positive. But there are no other forces with moments, which means rdy is a pretty easy solution. 1 times something is 0, so that something better be 0. Rdy is 0. So we've got another number we can go back into our table and plug in. Rdy is 0. If we go back up into our y direction equation, that actually helps us solve for rby. Since rdy is 0, rby must be 0 also. You've got rby plus nothing is nothing. Negative rby must be 0, so rby is 0 too. So rby is 0. So we've got another number we could fill into our table. Then we've got negative rbx plus rdx is 0. Well, we know rbx. If we go back to our table, rbx was 32.633. So we have negative 32.633 plus rdx is 0. So therefore, rdx must be 32.633. And that would be pounds. So we've got our x value for D, 32.633. And those are the 3 numbers that we got out of our horizontal member. In fact, if you look at the horizontal member, you might notice it's actually looking a lot like our truss members, like our regular truss member. In the truss members, we only exerted forces on the endpoints. There are no forces in the middle of this beam, which means this has to be a 2-force member. The forces on it must be equal in opposite directions on the endpoints. That means the y directions must be 0. which is exactly what the math told us. The y direction forces had to be 0, and the x direction forces had to be equal but opposite. And that's what they ended up being. So we got numbers for those. We only have one number left to get. So we go back to our unused equation. We had RBY plus RCY was equal to 29. RBY is 0. So RCY must be 29. 0 plus RCY is 29. So RCY must be 29. So there we go. We've got everything filled in the table. We just need to figure out our magnitudes. So we do our squares of the components, add them together, take the square root, ignore the sign, save yourself the trouble of getting burned by your calculator. So here for the A reaction, I'm just putting in 43.5 squared plus 29 squared. Adding those together, taking the square root, I get 52.280. The magnitudes always need to come out positive. If somehow you end up with a non-positive magnitude, you screwed something up. You don't have to do any work for anything that's got a 0 component. It's just going to be 32.633. Over here, same for D, 32.633. And then we've got 32.633 squared and 29 squared. That gives me 43.657. So there we go. There we've got our magnitudes at each of the pins. Yep, go ahead.
RCX. Apparently, I got lost somewhere on that.
Okay.
Can you go back to that?
Yes.
I've got a different number completely.
Different number completely. Okay. So let's go back to that. RCX came from the moment equation, or came from the vertical member.
Yep. I've got RCX plus RBX plus RAX plus 43.5 equals 0.
Yep.
Which solved out to RCX plus RBX plus RAY, or RA, maybe that's where I screwed up.
Yeah, over here is our x direction equation. We had RCX plus RBX plus RAX plus 43.5. Those were the four forces, horizontal forces. Then the y direction equation. We had
AX equals negative.
RAY, RBY, and RCY.
Okay, maybe that's what I did. Maybe I put RAY value instead of RAX.
Okay.
So that would make it 43.5. Yep, that's exactly what I did.
Okay.
Okay, found it. Thank you, sir.
All right. Any other questions?
Yeah, real quick.
Go ahead.
For when we found RBX as 32.633,
Yep.
you immediately filled in our CX as the negative of that, 32.633. How did you find
Well,
that?
I didn't immediately do that. I let the math tell me that. So let's go trace that through.
Okay, that's where I got lost. I didn't see
Okay.
that part.
Let's see that here. So right here is where we got the RBX. By the way, can you answer a quick question for me? Can you
Sure.
see what I am pointing at right here?
Yes.
Okay, there's the display over on this side is showing me the participants in the class, and I wasn't sure if that was getting transferred.
Right. Yeah,
All
I
right.
have that on my sheet. I got
I've been
it.
trying to avoid it. All right, so we've got RBX right here at 32.633. So that came from the moment equation.
Right.
Then I went up to the x direction equation here. In the x direction equation, I had RCX plus RBX plus RAX plus 43.5. Those are the four forces there. I used the fact that RAX was negative 43.5. So I had negative 43.5 plus 43.5.
Right.
And that was equal to 0. So RCX plus RBX was equal to 0. that just simplified that equation down. When I plugged in that RBX was 32.633, that says RCX plus 32.633 equals 0.
Got
So
it.
what can I
Okay.
add to 32.633 to get 0? It'd have to be negative
Right.
32.633.
I got it. Yeah, I don't know. I must have been sleeping at that point. All right.
That's okay.
Go ahead.
Totally understandable.
I got
Any
it.
other questions on this problem?
Just for clarification.
Yep.
RCX that does say 32.633, correct?
Yeah, I drew my table a little small there. It does say 32.633.
Just making sure I didn't make round off error or something.
No, I just ran out of space with that negative sign. And then, of
Gotcha.
course, if we were doing a real problem here, we'd round it off to, let's say, 3 sig figs in the end, just to bring those magnitudes down.
Gotcha. We're gonna burn through some paper doing these.
Yeah, but the math isn't as long as you can keep track of the signs and keep track of the equations, and of course, watch that that whole mirror image for shared joints in your free body diagrams. The math isn't terribly difficult to work out once you've got the equations down.
No, it's
No
not too
sines,
bad.
no cosines, anything like that. So once you get them, they're really not too difficult to work out. Any other questions on frames? All right, so that was that problem there. And next time, we're doing kind of a combined practice session, I suppose. So I'll review frames. I'm sure there'll be a question on the homework assignment. I'll also be posting the frame homework assignment, although the frames assignment will be a bonus homework assignment. It's going to be due on the same day as our exam. So it's not going to be a required assignment, but a good one to practice on anyway. And we'll do some more practice problems on trusses and frames. So method of joints, method of sections, and frames. That'll be all that's on the next exam, by the way, is just method of joints, method of sections, and frames. All right, anyone have any questions? All right, well,
No.
that's the end of the lecture component for tonight. If you are heading out, I'll see you Wednesday night. If you're sticking around, we're gonna put up another frame problem to play with. So have a good night.